lesson, we will be talking about nodal analysis. In the previous videos, we have discussed the concept of KCL and KVL as a method of analyzing our circuit and calculating the voltages, current, power in each element. In the previous lessons, we have discovered that in order to analyze electrical circuits, we have to be very familiar with the fundamental laws or foundational laws of electrical engineering in general. So for example, we need to know how to use Ohm's law and Kirchhoff's law. So specifically, Kirchhoff's law deals with the concept of analyzing elements in using nodes. That is what we call the KCL, and as well as loops, which we use the KVL. However, as mentioned, it should be noted that the techniques presented by Kirchhoff requires intensive algebraic calculations, since the number of equations needed is dependent on the number of branches in the circuit. To address this concern, the node analysis simplifies the process by choosing node voltages instead of element voltages as circuit variables. Since the number of nodes are always less than the number of elements, nodal analysis reduces the number of equations one must solve simultaneously. But before we proceed with the process itself of nodal analysis, we have to first define what do we mean by node voltages. So if you remember in our lesson in Kirchhoff's law, we have defined node as a point of connection between two or more branches or elements in a circuit. So it means for the circuit shown, there will be 4 nodes. We have node A that connects the 7-volt source and the 4-ohm resistance. And we have node B that connects the 3-ohm resistance and the 3-volt source. The node C that connects the 3-volt source and the resistances of 2-ohm and 6-ohm. And of course, the node D that connects the 4 elements as shown. However, we can further reduce this number of nodes in terms of our KCL by removing our node A, because we don't need to apply KCL in node A because we already know that since the 7-volt source and the 4-ohm resistance are in series, then their current should be equal. So there's no point in using KCL at that point. Therefore, in this particular circuit, we only have to consider 3: the node B, the node C, and the node D. So in order to understand the concept of node voltages, we need to be reminded that voltages are the potential difference between 2 points. Therefore, the value of voltages in a point is relative to the reference point for which the measurement is being measured from. For example, if we are talking about VAB, then it is defined as the voltage from point A to point B. And we also know that it is the negative of VBA, which is the voltage from point B to point A. This concept of reference point is essential in nodal analysis. Nodal analysis measures all node voltages from a single reference point. So instead that we measure it from VAB, then BBC, etc., then we just use one single reference point. Hence, it is essential to identify a single point or node in a circuit for which all node voltages are measured from. So to illustrate this point, we can consider once again this circuit that we are presenting. If we choose node D as our reference point, then we can say that VAD is simply the voltage from point A to point D. And then we can simply call it as VA, or the node voltage at A as measured from the reference point D. Similarly, VBD can simply be called VB, or the node voltage at B, and VCD is simply the node voltage at C. But this can only be accurate if the voltage at node D is 0. That is why in nodal analysis, the voltage at the reference node is always 0. So now that we have introduced the concept of node voltages, we are now ready to proceed to the steps in applying nodal analysis. Let's discuss the steps in determining node voltages using nodal analysis. Suppose you have a circuit as shown. The first step in the nodal analysis is to select a reference node and label it as the circuit ground. Or sometimes in other books we call it the earth. In choosing the reference node, it is wise to select the one with the most elements and or the one with voltage source connected to it. So we may use the symbols as shown, but we will be using this particular symbol which we call the chassis ground. Once the reference node is selected, the next step is to assign voltages to all non-reference nodes. In this case, we have two. Note that we have no longer considered the node between the 7 volts and 4 ohms as stated in the previous section. We have VA and VB. So in this particular circuit, we only need to solve two node voltages. So instead of finding total of 4 elements, we will be just solving for 2 elements, which is the node voltage A and node voltage B. Now that we have assigned the node voltages, we can now apply KCL to each non-reference node. So we have to apply KCL at node A or VA, and we need to apply another KCL at node B or BB. We now know that I1 is entering VA, so that's positive. I2 is leaving VA, so that's negative. I3 is also leaving VA, so that's negative. So our equation is I1 minus I2 minus I3 equals 0. For node B, I3 is entering, so that's positive. I4 is leaving, so that's negative. And 10 ampere source is entering BB, so that's positive. So our equation is I3 minus I4 plus 10 equals 0. Now that we have our KCL equation, the next step is to use Ohm's law to express the branch currents in terms of the node voltages. Remember that we are looking for the node voltages VA and VB, not the currents. So therefore, we have to express the currents in terms of the node voltages. But how do we do that? We do this by using the principle of the Ohm's law that I is equals to the voltage drop on the element divided by the resistance. But the voltage drop or the voltage on the element can be calculated in terms of the node voltages. We just follow the principle that V higher minus V lower is equal to the node voltage in the element. For example, in R1, which is 4 ohms, so for I1, we have a supply voltage of 7 volts. Therefore, based on its polarity, the node voltage between the source and the 4 ohms will also be the potential of 7 volts with respect to the ground, of course. So therefore, I1 can be expressed as the 7 volts minus the lower potential, which is VA, all over 4. Note that we assume that VA is lower potential because the direction of the current is from the 7 volts towards the VA. The direction of I2 is from VA to the ground. Therefore, we can say that VA minus 0 because it is on to the ground, all over 3. So therefore, I2 is simply VA over 3. For I3, we can observe that the direction of the current flows from VA to VB. Then we can say that I3 is equal to VA minus VB over 4 equals to 0. Now we can simplify this equation by simply multiplying this by 12. We can have a solution that says 21 is equals to 4VA plus 3VA minus 3BB plus 3VA. And finally, we can say that 10VA minus 3VB is equals to 21. This will be our first equation. If we use the same concept for node B, then we can also derive the following. I3 minus I4 plus 10 equals 0. I3, we already know that it is VA minus VB over 4. And I4 is VB minus 0 over 2. Then we just substitute that. Simplify this by multiplying by 4. Then we can arrive with the answer of VA minus 3BB equals negative 40. Now that we have two equations and we have two unknowns, the VA and the VB, then step 5 is to solve for the node voltages using simultaneous equations. So after simplifying the equations, we can now use algebraic techniques. So we can use a method of elimination of substitution, Kramer's rule, Gauss-Jordan, it's up to you. In this particular example, we will be using the method of elimination and substitution. So we have two equations, that is 10VA minus 3VB equals 21. VA minus 3VB equals negative 40. So if we subtract the two equations from each other, then we can solve that 9VA is equal to 61. So therefore, VA is equals to 61 over 9 is equal to 6.7777 volts. So now that we know VA, we can substitute that back to our equation number 2 and we can solve for BB. BB is equal to 15.5926. Therefore, the values of VA and VB are 6.77 volts and 15.5926 volts respectively. Once that you know the node voltages, You can proceed to the next step if you still need this. That is to solve for element voltages and currents using the node voltages. So suppose that we need to solve for I1, I2, I3, and I4, then we can simply substitute the value of VA to the original values of I1, I2, I3, and I4 as expressed in terms of the node voltages. So for example, we know that I1 is equal to 7 minus VA over 4. Substituting the value of VA, so that is 6.777. Therefore, we can arrive with an answer of 0.0556 ohms. Similarly, for I2, I3, and I4, we can do the same and arrive with the following answers. We can also solve for the node voltages if we want to. We can simply use Ohm's law if we want to use that. So in the next sections, we will be trying to solve for several problems with different configurations in order for us to see how nodal analysis works on different configurations of circuits. See you there.